this logic expression, we can check whether or not the final code or final inference is true or false, or final answer is okay. So it is just based on this. And in other things, just just here, just to show you a little about this as logic expression. That means how to expression or how the know. That means when we know that the machine code is just the program code. Sometimes it also have the high program code or middle program code. Sometimes it is just the low program code. Machine code just the machine and just know that the computer, it is a computer machine, just the circuit is hardware. So how to express or how to just using the hardware to define the software, the logic, and this way because it share us about this idea. And here we just share about the three the basic logical operator, not, or, and. And these three the logic operator is the basic logic operator. And we just want to know what's the hardware expression or hardware to express about this logic expression. The question is a logic operation, logical. But with logical variable, the P or Q is easy to describe in the hardware, particularly in high level or low level circuit. So we also know the zero and one. But how to describe in the computer for this not problem? And it's just using the circuit. If the circuit maybe you can have learn with the circuit course, you can learn about the circuit.
What languages uses logic gates? So there are three logic gates. The NOT gate is called the inverter, which I think can sometimes unfortunately others don't have a superhero holiday, so feel free to have things fun at home. But the NOT gate, again called the inverter, takes just one input. This is our NOT gate, so it's just a triangle. And the output is the negation of our input. So that's the NOT gate, which of course makes sense. Then we have the OR gate. And the OR gate is going to take two inputs, and the output is going to be the disjunction of those two inputs. And then, of course, we have the last one, which is the AND gate. And the AND gate also takes two inputs. Notice this one is straight here, while the OR gate is curved. And the AND gate will have an output of the conjunction of the propositions, which is, of course, the AND gate, whereas the OR gate is this one. For our first example, I've set up a logic circuit for you, and what I want you to do is determine the output of each logic gate, and then, of course, the overall output. So we're going to go through this one together, but this is just good practice. So notice P is going directly into this AND gate. And I've given you the little cheat sheet up here at the top so you can see what the three are, because you probably don't have memorized it. So we have P as input to the AND gate. But here, for Q, notice Q travels through this guy into the So here I'm going to have P and not Q. And then that's what's going to go in here to my OR gate. So this is an OR gate. Now, what else is going into the OR gate? Let's see what here we've got OR. It's going into a NOT gate, which means my output here is not Q. So into my OR gate, which is this one, I've got P and not Q, or not.
So from this, just the picture, we can know that in our computer side or in the hardware, the computer just using this the circuit, the picture or circuit, the graph to describe our just the logic expression. So the logic expression for our human, maybe you just can be seen. You can write down just like the formula expression. But in the hardware, you just have it using this many with logic the circuit or logic gate. With logic gate combined together. So that is why you will find some hardware the platform just have many circuits. And there's many circuits for each of the circuit just describe some the logic expression. And each of the logic expression just refer to some the real world meaning or just the natural language meaning or just our human language meaning. So this logic expression just have the this display in the computer in hardware. That means in hardware just this logic circuit get or circuit picture.
So that's everything that I would have to do here. This is the overall result. But to do this correctly, you would have to make sure that you get each output for each logic gate in the circuit. This is our total output for the circuit. The example that we just did is pretty straightforward and nice because they do all of the work for us. They make the gates, they make the lines. All we have to do is flip the outputs. This one's going to be a little bit harder. We actually have to construct the circuit ourselves. So again, I don't expect you to be really perfect. I certainly am not, as you can already tell. But I'm going to go ahead and create a logic circuit here for P and not R, or not Q and S. So I've got four things happening. I've got P, R, Q, S. So anytime I see a not kind of thing, I'm going to go ahead and put that triangle in there because that's going to tell me that it's a not competition. So P and not R. So here this gives me not R. And again, we're looking for the and gate. So that's going to be this one. Now, when you're drawing these yourself, when you're drawing these yourself, you don't need to put the outputs like we did on the last example. However, it might be helpful for you just to keep everything straight. So you can write the not R, but you don't have to. And you can write the P and not R if you want to, but you don't have to. The Q and S, you can have to leave them. And here, again, this makes it not Q. So here I've got not Q and S. And again, these parts are white with the exception of the gates. Not Q and S. Those parts are white don't need to be written, so the outputs don't need to be written. Notice now I've got my P and not R. I've got my not Q and S. And in between those, I have so now I'm going to make an OR gate. Instead of making a giant OR gate, And as you're drawing this, really what we're looking for is, can you do all of the parts in blue, and can we change these three colors? So yellow, all of the parts in white, parts necessary. So as you're drawing it, if you're constructing it, you're really just looking for the actual circuit itself and the output, as long as your outputs make sense. And start by just taking a look at some competition. I've given you the little cheat sheet up here.
So from this video, we just to show you about the logic expression can be just give the one-to-one map between this logic expression and the logic, the circuit or circuit picture. And that means if give you this logic gate of this circuit, we can to write down Unicode logic expression of this logical gate is determined. So we can each this circuit, the picture refer to each one the logic expression. And the other way means that if you give you the logic expression, we can finally here and write down or design just the final the logic circuit or this the circuit picture. So that is this just to show you in the computer layer or machine code or hardware. It's just using this hardware circuit to describe our the logic expression. So this is the difference because in our human words or in our natural language words, we are just using our human nature or our the smart brain to understand what it means. This logic expression. That means it is just the many the logic symbol and then have many the logic operator and this operator just combine this logic symbol and then to finally compose some many of these logic expressions. But in the computer world, in computer baby, this baby world is different for our human baby. It means his brain or this computer machine, he just the code, the circuit. That means he just many of these circuit for this for example, for this logic expression, it didn't have any of about this just the meaning of the symbol meaning of this logic operator. It just have this circuit, and this circuit just maybe it is higher value or low value, just depend on its different this circuit. And some many of these logic operators refer to this the circuit gate. So operator refer to circuit gate. So this is a different expression. So based on this different expression, then if we want to discussing about what's their computation for this logic expression in the computer world, and sometimes how to do the computation in the computer. In fact, they are just translated into each computer translated into each inference. But not the circuit can be do some inference. Because inference that means whether or not this circuit can be reached. That means it can be reached. If it can be reached, it can be okay. That means it can be get the truth. If it get will be true, that means it is the inference can be okay. We can just get our the final result. If it's not true, that means this circuit path is not, it cannot pass into this circuit. Then we can say this inference is not true. So that is the difference. In the computer world, that only can combine true or false. So we are just to say it is the inference. So in the computer world, we are just to do the computation as inference. So from this session, we just to talk about the role of the inference. Okay. Now we should to understand the basic concept. First is proof. Proof, it is maybe want to just say, you want to just give the idea or give the evidence that means it is true for some result. And the argument, this argument it can be seen about some similar as a parameter. And valid, valid means that for some of the conclusion, it is can be for the special cases. That means if you just find special cases satisfy your result, we can say it is valid. Okay, so it is just for this with the basic concept. And okay, here just some uh, expression for these rules of the inference, and maybe it is just from this premise. Premise, we can say the condition. It is here we just to yes, it is a condition. For example, we have just give you the condition one. That means if it snows today, then we will go skiing. And the condition two, it is snowing today. So based on these two conditions, or based on these two premise, what are concluding. And if we just get a conclusion that we will go skiing, whether or not it is true or it is okay. So just based on these things, we can just do some inference. So if you want make the computer to make you to do this inference, how to translate? Well, this is the natural language. So for this natural language, computer cannot understand. So first, you should to translate this each of the condition or premise into the logic expression. That means this is logic expression, and also the logic expression, and concluding we also to as the logic expression. So based on these two logic expressions, we want to influence whether or not this conclusion logic expression is then computer can understand. That means you should to just translate this. So first we just have this just this translate or these rules of the inference. These rules mean that if you have the two, we just using this bar and this over the bar, we just say the condition or premise, and the over the under the bar, we just say it is conclusion. Means if we have P and if P then Q, P condition Q, and based on this, we can infer Q. It's just like this. But this can be seen as inference. So from this conclusion, or from this inference rule, we can say if we have premise P and P condition Q are both true, then Q can only be true. So, also to from this truth table can understand this inference rule. And here is some example. We will just to show you some basic this example in the video. Now we just to about the video, maybe it's concrete. Say it's inference.
Before we start talking about the different ways of inference, first let's talk about purpose. Purpose agrees with arguments or as valid arguments where logic is used. So arguments is just simply such that if A1 and P2 and P3 and A2
So from this concrete understanding for this argument concept, you could say that the argument is a preposition variable. I know that preposition in our previous session, each preposition refers to a simple sentence. Because each of the simple sentence can be, it is understand that just to describe some meaning in our human world. Because we know that we are just using the natural, especially the simple sentence describes something. For example, it is raining in the sun. It is a simple sentence. That it just describes some this condition for this can be seen as argument. The argument is just the prepositional list or prepositional sequence. Condition without the proving. So the valid argument is that we can from the premise or from our condition we can influence our the conclusion. That is means the premise imply or influence our the conclusion. Means from many of these we can influence it to or means this logic expression can be true. Either this can be true. Always the knowledge. So, if not to translate this expression or this natural language into logical expression, maybe you can say it is an optional propositional. That means it is the philosophical the idea. That means if you have a strong logical expression, then you can to say something about this logical sentence. You can relate this philosopher. So philosopher just to describe this thing, but if we just to model these many of the things into the logical expression, then all of us we also can be done well, just as a philosopher idea. So this is a symbol. We have 3 points and just say and so therefore.
and Q. I'm sorry, if P then Q and not Q. If all of that, then not.
So just from this idea, maybe we can to know that what's the computer to do the computation, or what's the computer to do the inference. So from this ways, people from our human world or from our natural language meaning, that means it is easy to understand. That means, for example, if P then Q, we can just, in our human world, maybe it can be seen some the theory. For example, the physical theory, the mathematical theory, have many theories already to show that it is true. That means if we have this P condition, then we can choose this is the true. And now we tell you that now we are certifying your condition P. We have P. So we just this conclusion Q. So it is no problem for our human. It's easy to understand. But what's the make this word to let the computer to understand this is the word? Because we know that the computer only can understand the logic expression or this programming language can show that. And this logic expression can be seen as the hardware circuit. So we should to translate this idea into the logic expression. That means what's the inference also to be as the logic expression. That is just using this condition symbol. That means this condition symbol can be seen as an inference or imply. So that means for all the just the condition of parameters and this just combined with the junction and all of them together, and the conclusion we just use this, and we are using the connect this just the operator or just the condition operator for this error to combine together and make the computer to check whether or not it's always true. So this it can be done for the computer. So this idea we know that computer just do their inference and they check whether or not is the like this or like this expression is the technology that means always true. Just to check it is true, always true is easy. Just using the true table, no problem. Okay. So from this picture in this video, we can just have notice have two ideas. The first is computer to translate the inference work into to determine some the special logic expression is always true. Okay. And the second is this left side is how humans uh, just do some the proof. For example, even make your proof in the mathematics or high mathematics you have already learned in the previous course or previous semester. Then we have you already learned. You are just to do some the proof that means from the premise or from the condition already given from the just the question kind. So this question you can do many some just the condition, and then from this condition you just do some inference to find the result. It is just the can be the direct proof. And the right side means it is also have this theory or also have this or existing the words, and then but we know that is not true. Means the final conclusion or final answer is not true. It can be seen as just the indirect proof. Indirect proof means that we first to show that it is the final answer is not true, and we to inference it is a crash or it is just not true for the condition. So it is also the family for our just the humans group way. And in the nature, we also to discussing about this well. So just from this we have noticed two um, notice. Okay. First is computer to translate inference into the logic expression whether or not it's always true. And second is these two sides have different the proof way. The first is direct proof, and second is indirect proof.
Transfer property says if A implies B, B implies C, then A implies C. And that's exactly what this is saying. It's saying if P implies Q, so if it rains, then I'll need an umbrella. And then if Q implies something else, if I need an umbrella, then maybe I should wear golf shoes. Then the conclusion is if P and R, or if it rains, then I should wear golf shoes. So that's all it's telling us is with one implication essentially leads to another. So how would I write that as expressed with P? Then write my premises is if P and Q and Q and R, but I'm saying if that's true, then the result is if P and R.
So from this way, you will find this and this P condition Q, Q condition R, and P condition R. It is just already true from this question or this already. And this symbol they just add from this condition to the conclusion, and using this condition to add this another condition symbol to make the computer to check whether or not the final compound logic expression is always true. So this symbol, this condition symbol, just to make the computer to the compound. That is why they needed that computer to do their inference just to check or just to translate into logic expression. Just like logic expression to check whether or not it is always true. Just like this. And maybe it's also easy to understand for our humans because it is a condition statement can be these rules can be propagated. That means can be pushed back P condition Q, Q condition R, then P condition R. So it is easy for our human, but computer cannot to understand this push back or just the propositional. He just only to understand the logic expression. So you should to translate or change to this inference path of question into this logic expression. Just add all of the premise should be careful. There are different the premise using the and. And then from this the bar over and under we're just using this symbol logic. This is just the operator condition. That means from this premise, many of the premise to inference to this final.
Then we have the disjunctive syllogism again because this is disjunction. Again, we're saying P or Q, and then not P. So we're saying P or Q occurred was a P, therefore it was Q. So again, this makes a heck of a lot of sense to me because if we're saying that P or Q must have occurred, but P didn't occur, it makes sense
So from this, just the cases or this example, just means that it is addition, or the addition rule means that we can just for the existing P to all other ways. And then from this, we can just influence this, no problem. Means we can just influence, if we have P, so we can say P or Q, no problem. Okay? So from this value, we just mean that if it's just addition, that means that to check P, addition P or Q is always true. So if you just using the truth table, you can influence, you can to check it's always true. So we have this rule, addition rule. So we will find many of these addition rules just similar as this. We also to give you this the way also this disjunctive this rule, and also to have this just have the special rule. That means P or Q, but now we can say not P, so we only to depend on Q. So it is just mean that P or Q and not P, P or Q, not P. So you can just only get the Q inside Q. So inside these words or influence these words in the computer, you cannot understand what it means inside. But you can understand we make you to logic, combine logic expression with this condition symbol and to check whether or not this final logic expression is always true. If it's always true, it is okay inside. So for our human, we can understand well because P of Q, now we are just get and just remove P, so only Q. 5 minutes break, okay? Okay, we continue to talk about this inference. That means we know that the inference is different for computer or computer world or our human world. That means just for this example or this rule, that means it is easy or can be easy to understand for our human because it is a popular philosophy question. That means we have the condition T, and we also have this the rule or have the theory, or this can be from our the practice idea. That means if P then Q, then we have already P, and we know that if P then Q, so we have Q. This is the problem. But how to teach the computer baby or how to teach the code machine to understand this philosophy idea? This is maybe sometimes it's boring, but no problem. We are just change because we know that the computer can understand the logic expression well. So we are just combine these condition or premise together using and to combine together. This is all the condition. And this conclusion just refer to this conclusion, and this can be seen as just all together. So we are finally use this condition operator to combine together, and all the premise as the conditions statements of the premise, and the finally conclusion as just the backward or just the right side. So we are just add this and, or we also just add this condition symbol together. And that means we are just to translate this inference things or task into the logical expression. So you can find just this inference things also can be described as logical expression. And now we're just to check whether or not this logical expression is like this. This logical expression is always true. Now, here we just to give that it is always true. So if from this truth table, we find it's always true, so it is okay. So that is the difference from the computer world and our human world. That means our human world, we just think it over, think it deeply, think it and think, and to get the final conclusion. But in computer, is maybe simple. First, be sure to translate all of them in logical expression. And then, based on this logical expression, I just want to check whether or not it's true. It's like this. We are just for this symbol, we just to translate this condition. Okay? And then we are inference or imply these words. We are just to check this final logical expression is topology. Whether or not it's always true. If it's always true, that means, okay, no problem. It is okay. So in the computer world, he cannot understand what it means, this symbol. Therefore, he cannot know this the circuit, this hardware circuit for this. But he only has this condition. But we know that we have already to show that in fact there are only the three gates. This three gates means it's not, it is the and, it is or, and or gate. We have to tell you for this gate why. Because in fact in the logical equivalence we have already to let you to remember that P condition Q is logically equivalent, not P Q. So we didn't to design the force the circuit the gate for this condition. We just to using this not P of Q. We didn't need this this force this condition gate. We just using not all to describe this gate, this condition gate. That's why we only to choose three precedent. certificate is okay. Now we continue to our video to the more about this for example is the influence of the addition and simply. And addition we have shown that means if you have P, then we can just have P or Q. And other things, if we have that means if we have P and Q, then from this we can define. You just say you have the stronger condition P and Q. So for the strong condition, we can just say one of them is okay. So P is okay or Q is. And in otherwise means that if we just to describe this logic expression that P and Q condition P is always true. Just similar as additional rule. Additional rule means that from P condition P or Q, this logic expression is always true. So if we just already to give this inference or to determine or to check this is always true, then we have this rule additional. So this additional rule is for argument. Or sometimes you can say it is just the database. This is the database rule, the rule database. So for each rule database, just need have a special logic expression. This logic expression is always true. So we just but for argument, we write down this stuff. The computer cannot understand this stuff, but we understand this logic expression. So he said this logic expression is always true. So for this, maybe some is stranger, but it is very okay. That means P and Q, we can condition P and Q.
Two, if John works hard, then he isn't having any fun. So isn't having fun. So if John works hard, he's P. If then, that's K John. And he isn't having any fun. John is having fun. It's Q, so it's not Q. And then three, if John isn't having any fun, so not Q, John's not having fun, then he won't make any friends. So it would be not R. So these are all premises I used in my arguments. And you'll notice I'm maybe not just going to front them because a lot of people like to front them. And by that I mean, I'm just going to write all of those things and forget them. I don't do that because I'm going to write them as I need them. Now, the last thing I'm going to do before I get started is I'm going to go ahead and take a look at the conclusion. John will not make any friends. So my conclusion should be not R. Now, it's good to know all of that before I get started because then I know what I know. I know what I know, and I know what I'm trying to get to. So let's get started now that we are ready. So we had to do a lot of steps to get ready. Now we're ready, so let's go. Step number one. Again, my first step is really always going to be preface. So here I'm going to say P because it's preface. I'm also going to say if P, then not Q, which is preface.
This premise means that it can be get directly from this fetching instruction, the fetching condition. From this fetching statement, we can directly to translate this or directly to get this condition or premise.
Here, we're going to use a law. So notice I've used this guy and I've used this guy. I haven't used the last one yet, and that's okay, because what I'm doing is I'm saying, here's two things that I know to be true, and here's some conclusion. So if I know if P then not Q, and P is true, then not Q is true. And that's what I'm going to call this sentence. And again, whenever I'm giving a law like that, or a rule of inference, I'm going to give the numbers of the statements that I use. So I use the first and the second statement to say the law.
So this is just maybe the style, maybe in the homework you should also just similar write down like this. That means first we are just the number from 1 to 3, and the second column just means it is the logic expression, and the third column is just write down reason or why you just get this logic expression. Promise me that we can get or directly translate from the fetching statement. And these others, for example, these the three logic expression. The third logic expression is based on the first and second logic expression, and using these inference or imply rules, models occurrence by two. So sometimes you can use the simple. For example, you can say it is from 1 and 2 using some the rules. Sometimes you can to describe the whole.
From there, I'm now going to say, hey, guess what? If not Q, then not R. And this was a premise. So now I've used that last premise, but notice I didn't put it in the beginning. I didn't use it until I was ready to. Because now what I can say is if I have if not Q, then not R, then I know not Q is true. And that's right, I can say not R is true. And the reason I can say not R is true is promise goes 1, 3, and 4. And again, that's exactly where I was trying to get to, is both not R is true.
So this can be seen as the proof procedure or proof the sequence. but we just list this the simple style. We otherwise you will just write down, for example, if we just do some proof in your arithmetic, maybe some maybe you should write down many the words or many the natural words such as because we have P and P condition node Q from the fetching, and then based on model occurrence on these the two expression, then we can inference. Maybe you can write down many things, but if you just use this style, it is easy and maybe simple for you to check whether or not it is okay. And also even for other people to read about your inference or your proof process. Okay. So yeah, just in comment or comment you following to just do your proof like this. Okay.
Here we are going to show that the argument with premises P, if P and T, then or S. If Q, then U and T. If implies P, not S, Q. These are all premises. That those will lead to the conclusion that if Q, then R is R. So I know when I serve a question like this, it's a little bit more trouble. What do I know?
So if it let you to shoot or let you to do something proof, because for our human, maybe we are easy to understand or easy to using this just the existing the rules to do our writing to us. But if you don't want like this, you can just for computer machine, you can write down all of them, you can together all of them, and condition to the conclusion and to make the computer to check whether or not it's always true. It is okay. But it is maybe is boring for our human. So for our human, maybe we are just to using the step by step as the existing rules.
Oh, what do I not know? What am I trying to get to? So of course, what I'm trying to get to is my conclusion. Here's where I'm trying to get. And I've got 1, 2, 3, 4, 5 premises. So right away, we know we're going to have quite a few steps in this logical argument. So let's get started together and see how it goes. I'm going to start with 1 and 1. I'm just going to say Q. So Q is true because it's a premise. So what else can I say? Well, I'm going to say if Q, then U and T. Again, a premise. I'm going to move these over a little bit just because I haven't given myself a ton of room. So premise and premise. So that's this premise and this premise. I've used both. Now, why would I use both of those? Well, because I know that if Q, then U and T is true, then and Q is true, therefore U and T is true. So how do I know that? Yeah, that's right. Modus ponens on 1 and 2. So how does that help me? Well, let's think about what I can do next. If I know that U and T are true, then I should be able to say that U is true. And I should be able to say that T is true. And I can do that by simplification on 3. Same here. So now what? Well, I'm probably going to take a look at another premise now because I've sort of gotten to the end of what I can say so far. And I have one that says if U, then P. So let's do that next. If U, then P. And that's a premise. Now, why would I need to know that? Well, if I have if U, then P, and U is true, then my next step should be that P is true. And why is that true? That's modus ponens. On 4 and 6. So P is true. Now think about what I haven't used yet in my premises. I've got P and T. Well, I just showed that P is true. Over here on step 5, I showed T was true. So step 8 is going to be P and T. I don't really need the parentheses, but you can have them if you want, either way. So P and T, and how am I able to show that? That's a conjunction of 5 and 7. So now that I've shown P and T, then I can say this premise. So I'm just going to recopy that premise. If P and T, then R or S, and that's a premise. And then for 10, I'm going to say, hey, guess what? R or S is true. How do I know R or S is true? Modus ponens on 8 and 9. My pen stopped working for a second. 8 and 9. All right, so I'm getting close. I'm trying to say if Q, then R. And remember, I started with Q, and my very last step should then be R. So 11 is, again, the last premise that I haven't used, not S, which is a premise. Then 12 would be, remember this one is saying R or S is true. And then it says, guess what? S isn't true. So what does that tell me? That tells me R must be true. And that is the disjunctive syllogism.
So just from this, you will find if you just for our human, because we know we are just the human to make to clear or make to understand many of these rules, how to use the existing rules to do some proof is no problem. And just based on this existing rules, we can do out this inference very quickly. And if we just using the truth table, maybe just combine it together and using truth table, it is also okay, but maybe it is have a non-side, have maybe it sometimes is very boring for our human, but sometimes it is just maybe it is very quickly for computer maybe. So we have the two ways to do some the proof, just as your homework one. Homework one just to let you to show something to do some proof. That means you have two ways. The first you can using the existing the logic equivalence rules, and the second, you can use the truth table. And similarly, if we let you to show about the imply or just do some this the inference, you also have the two ways, because we know that this imply or inference work or inference the question also can be changed to this logic expression. That means all the program is we just the conjunction combined together with the and. Then condition to the conclusion, and this combine this the whole logic expression, and then we are just check or determine whether or not this whole logic expression is always true. Be careful, it is always true. So always true, just as to show some the logic expression is just for no always true. Just means it is to from the definition. If always true, that means that it can be work for the imply or inference. So we are just translate the imply or inference to the logic equation with the condition symbol, and then to check. So we also, if we don't want using this truth table because it may be boring, have many things you should to determine all the possibility value. This is maybe have very boring for our human. So you can just using existing is the rules of the inference. And based on many of the rule inference, we can do step by step, just like this. Okay. And here just to show some many example to show what means these inference rules. And based on these inference rules, we can do many things. That means we can do some proof, or also sometimes we can do some the imply or inference. And here is the combine all together existing or popular rules of the inference. And also here is the rules of inference for our human. This is for our human. That means we are just using the bar, and over the bar is premise, and another bar is conclusion. We are just using therefore. And this we are just for the machine or for the computer. Computer just using this logic expression, you will find this column, all of the logic expression. And this logic expression should be tautology. That means it's always true. So this special logic expression have proved is always true. So we can say it is the rule of the inference, or sometimes we also give some the name. So here column, the first column and the third column is for our human to understand or to remember easily by name. Addition, simplification, conjunction, model column. So you will find we are using many of the modern columns for the videos, the examples, and have any others. These existing the inference rules. Based on this inference rule, we can do some proof and do some inference or do some imply by the computer. This is also the example we are going to do this. And now here is the homework 2. Now I will publish after class, online class. I will publish this in the homework in our Intel group. So similarly as the first homework, maybe you have 2 weeks time to finish your homework 2. And this question is just like this. If we from this maybe from this first the condition, and you will from this you will to get the final conclusion, and this final conclusion is wrong. Now let's check which step is wrong, and to get the finally is wrong. This is wrong, but if we just for each of the one, maybe you are saying it is okay, because A, B is positive integer. For example, from step 1 to step 2, here is equivalence. Equivalence, that is by condition equivalence, we need this A equal to B. If A equal to B, then A squared equal to A and B. So it is okay. Similarly for this, and if all is okay, then we'll get the wrong result. 2 equal to 1, it is wrong. So you will check which wrong the steps and give your reason. This is the homework 2. Maybe it's not difficult, but you should be careful to check about your this. Okay. And this is just say about this. But sometimes we should be careful about these rules of the inference. That means sometimes you maybe wrong your rules. For example, if P then Q and not this P, we have P, so Q is okay. This is okay. But if just using this, if P then Q, not P, so not Q, this is wrong. This is wrong. That means if P then Q, if not P, that means you can to check. That means if P condition Q and not P, this is all premise. And using condition not Q, maybe it's not always true. It is not always true. You can just use your truth table sometimes. And if for our human understand means that we say that if satisfying P, then you can get Q. But you say if not satisfying P, we cannot say if not satisfying Q. Here is a concrete example that if P means you do all problem in the book, Q is you learned descriptive math. That means you are just from if P then Q, but from this, that means if not P. Not P means that you don't do all the problem in the book. If you don't do anything, if you don't do all problem in the book, we cannot to infer that you don't learn descriptive mathematics. Why? Because maybe you have learned mathematics, descriptive mathematics, but you didn't do all your problem. Maybe for some other reasons you didn't do all the problem in the book. Although you just learned, of course, but for some other reason you didn't do all the problem in the book. So it is cannot say if not do you don't do a problem, you don't learn. So it's not wrong. Sorry, it is not right. It's not correct. It is a wrong rule. So you should be careful. That means it is also too easy to understand. That means we say P condition, we have no the logical expression is that P condition Q is logical equivalence, not Q condition not P. That means we cannot say is not P condition not Q. This is not logical equivalence. It only means that not Q inference or just the condition not P is okay. Just like this concrete example. That means if you do all problems in this course textbook, then you learned discrete mathematics. And if not learn discrete mathematics, we can inference you are not learn, so you didn't all the problems in the textbook. Means if P then Q, we can or just logically equal to not Q condition not P. But we cannot say not P condition not Q. They are different. Okay. Okay, now maybe we have 5 minutes the discussing time. Any question? And I just make notice that means the next Monday morning we have no class because of the Mid-Autumn Festival. Okay. Be in China, maybe we have a Chinese festival day. Okay. So next Monday we have no class online. And we will have this too. Any question? I will publish this homework to the Intel group. Okay. Any question? Okay. Okay, if no question, that's for today. And remind you next Monday we have no class. Okay. Bye.
老师，我也想到他按摩。
Okay. Yes, next Monday we have no class.
No, I'm asking about homework.
Then, sorry. What's your question?
My question is, we have second homework.
Your second what?
Homework.
Homework, yes. We have published your second homework in the Intel group. You cannot see?
No, can you send it in WeChat, please?
Oh, WeChat.
Mm.
WeChat cannot to do, you cannot to submit about your the homework you can submit. You cannot submit online on the WeChat. And the Intel group very easy. You can submit, okay, and also the teacher assistant can give your some score about your homework.
Okay.
I can remind on the WeChat group, but you should to submit your answer in the Dinto group. Okay. Any more questions?
No.
Okay, thank you.
Mm.
Bye-bye. That's all today.
Thank you.
Thank you, sir.
Hello.
Roshan.
Hello. Yeah. What's your question? Any question? Bye-bye. No question. Yeah. That's all.
再见，老师。
再见。拜拜。